So we're trying to make this continuous by plugging in k. What's the general idea behind these things?
Set them equal to each other?
Yeah. If we do that and then plug in 0, we have an indeterminate on whichever side you plug the top one in on. So how do we fix that problem?
Rationalize the top.
Yeah, we still have to rationalize, and it's still a limit problem, basically. So here's some work for that one. And you should have chosen A. Go ahead and take a look at the A, or excuse me, at the work.
How come you can just cross off the x in the numerator?
Because this 7 minus 7 is 0. So it's really just negative 2x over x and that. So you can just divide that off.
But wouldn't it be negative 1x?
Thank you.
Up here, you're saying?
I was thinking, I realized I was wrong, but I was thinking for some reason that it would be, when you cross them off, it would be negative 1, or negative x over whatever.
Oh, yeah.
But
Yeah, so those just, the x's divide to 1, and then leaves the negative 2. Yeah. Now, if the 7s hadn't canceled, can you do that? Like, let's say this was a 6 and it was 7 minus 6, and we had 1 minus 2x. Can we just drop the x off? And that's a common algebra mistake that, I'll write what I just said. If it was 1 minus 2x over x and something. You can't cancel those x's because of order of operation. Okay, so don't, make sure it's a single term before you just drop it off. If the 1 had some kind of x squared, then we could, but not just the way that I wrote it there. Any questions on that one? Other questions, I should say? How'd you do on it? Give me a thumb somewhere, since nobody said. Okay, so we're kind of, well, we're here and above, I guess that's good. Any questions on the homework?
Should I go right now?
No, I wouldn't even go during this class myself. But
Good idea.
yeah.
Well, I have English to talk.
Oh, I'll do it then. Okay, what's the story on the homework? Are we solid on it? It was, some of it was like this, right? 4, okay. 4. That one? Mm-hmm. Alright, so we're checking continuity at 2 different spots. How do we know if it's continuous? Yeah, so we need to check if, let's be very specific in the wording. Yeah, yep. Well, they have to match each other, but also the value, right? So we're looking for left and right hand agreement and matching the function's value at that point. So from left of pi over 2, from the left, we're doing cosine of x, which is what? What's cosine of pi over 2 is what I meant. Okay. This, by the way, yeah, this one's not too bad, but do you remember me saying, I think it was last week, if f is defined in the problem, you don't have to write it out. You can just use the word f, or the function name. So I could similarly just say f of x here, instead of writing, not, like I said, those are not that big a deal, but some of them are. So just a reminder of that. Anyway, so from the right side, we're going to do tangent of x. So this is tangent of pi over 2, which is what? what in terms of tangent, which one's on top? Sine. So this is sine over cosine. Sine over cosine of pi over 2. What happens with that one?
Pi over 0.
So it's undefined, right? Okay. Well, is that continuous there? No. So we don't need to go on and check the function's value, but in fact we kind of did anyway. But we don't need to if it's not going to be equal on both sides of our limit. Okay, so then same thing, but now we're going to shift from tangent to sine. So I don't want to write all that out again. If you can just say tangent. So this is coming in from the left. We'll have tangent of pi, and then we'll have sine of pi from the right. So maybe I will notate at least the left and right. So tangent of pi and right. We're going to do sine of pi. What is tangent of pi? 0. And sine of pi? Also. So tangent of pi is 0 because sine of pi is 0. And then, there we go. And then we also need to check f of pi. Which of these three pieces does pi go for the actual function value? Is it tangent or sine? It's the sine, right? It's the or equal to piece. So f of pi is sine of pi, which equals 0. So that one is continuous because we met all three criteria. The limit exists, the limit is the same, so it exists, and the function value is defined. That was our first criteria, but also it equals the limit. So does that help, Dutch? Okay. How are you guys doing with your trig circle, your unit circle? Okay. Well, you see how we use it. It's not like we get more into it than this. It's mostly just this kind of stuff. Any others on the homework that you'd like to do? Yeah.
Can we do 6?
6, sure. 6. You like the wording up here? The type of each discontinuities and where they are is located. Good thing this is not an English class. Alright, well, how do we know what type discontinuity is? Yeah, so limits can help us see if it jumps. None of these have denominators, so are we going to expect to see any asymptotes? No. How about holes? How do we make a hole?
0.
And numerator. It's got to be both, right? So we don't have that here. So really, we'll just see if there's any jumps. Sonia, are you good if we just talk through and I'll write a little bit, or do you want me to write the whole thing out?
I'm good.
Let me know if it's not enough. So from the left, our limit is, I'll write it over here. From the left, so 2 times -1 plus 1 is -1. Okay, and then at x equals -1, we're just given a single value. We already see that those are not the same, right? So there's going to be some kind of issue there. Coming in from the right of -1 is this whole thing. So -1 squared minus 6 times -1 minus 6. So what is it? -1 plus 6 minus 6. So we just get -1. Okay. So we have the same limit coming from both sides, but the function's value is not the same. So what does that say? It's a whole. Now I know I said we're not going to have a whole because of denominators, but this is a different backdoor way to figure that out, right? So far we know we have a whole at x equals -1. Okay, and then we need to check from the left and right of x equals 1. So same thing. Let's do a different color for those. From the left of 1, left of 1. Now we just plug 1 into this thing. And what is that? Negative 1 minus 6 minus 6. So that's negative 13. And then to the right of 1 is 3. So tell me about that kind. I know this is all over, but it beats trying to write it all out for just a homework check. Right of 1 is 3. So what kind of discontinuity is that? It's jumping, right? It's technically it's coming in down at negative 13 and leaving at 3, so it's jumping up. Jump. Don't forget to say where it happens at x equals 1. Does that help? Do you have any other questions on it? Any others? Test prep went okay? Okay. All right, well, let's press on. So now we're gonna, this title, by the way, remember these slides come from, actually from College Board, and I uploaded, at the beginning, I uploaded the CED, stands for Course and Exam Description, onto Google Classroom. If you ever want to look it up, this stuff is all in there, like these kind of slides. This title to me isn't very descriptive of what we're going to do. So maybe come back to it and rewrite the title that means more to you. Because what we're actually doing here is analyzing where any given function is continuous. That's kind of what we're doing. And we have to take its domain into account. So that's, the confirming word is a little bit weird in my opinion. So just to review, we have 3 criteria for our continuity to exist. So we have to have f of c exist, or it has to be defined. The limit and the function value have to be equal at that point. Okay? So if any of those falls apart, we don't have continuity. And that's what kind of what we were just looking at. So with those definitions, are any functions that are not continuous on their domain? Because now, I twisted that on you the other day and said, well, this value isn't in the domain, so yeah, it's continuous. So are there any functions that are not continuous? Well, looking at these pictures, you can see green and red brackets, which gives you a little hint. Are these continuous on their domain? Yeah? How about this one? No, because remember, that point is included in the domain, but it's not continuous anyway. So, not continuous, even though the domain is defined all the way, like from infinity to negative infinity. Speaking of, before we get into this, are you guys familiar with this symbol for all real numbers? Yeah. Okay, so you can use that. In fact, I would encourage you to write it both ways just for practice today. All right. So really we have 3 reasons why we have a domain restriction. Can anybody think of what they are? Meaning, here's a function, but it doesn't work here. And we have to say kick that number out of its domain. What can you think of where we run into mathematical trouble? What have we seen so far? Yeah.
I think one thing is any value of x that make the denominator.
Okay. Yep. So first one, denominator can't be 0. So when you go on the hunt for issues with the function's domain, that's one of the things you check. So like in that one, what would we have to exclude from the domain of that first function? -1. Okay, so it would not be in the domain. Anybody know what would happen there for that particular function? I'm gonna say everybody should know. Is it a hole? Is it a jump? Is it the other option? What would happen at x equals -1 for that first function? It's a vertical asymptote. Good. Hey, by the way, that reminds me. Did it? All right. What's another one that we can't do? You can see an example of it there. Yeah. So we call that the argument of the square root, or the radicand. You guys remember that word, radicand? It has to be positive or 0. It can't be less than that. So even roots of negatives. That's the next issue. If we have an odd root, like if this said cube root, who cares what it is? It's fine. But if it's an even root of a negative, now we get into the complex number system. So look for that. Do you guys remember the restrictions on logs? It might help if you think of the graph. I'll remind you. Remember, log is the inverse of exponential, so that's exponential, and log is the inverse of that, so it's mirrored, so it looks like that. Oh, that isn't very good. Let me try again. There we go. So what is it avoiding? Like, what will not, if you said log of this number, it would say undefined. What is it avoiding?
Negative.
Negatives and 0, actually, both. So log of anything less than or equal to 0. So log of 0 or negatives. So you'll have to keep your eye on that one. That one is going to be the trickiest case, because making something negative there's multiple ways to do that. Okay. I'm going to write out here these restrictions. That's not what I said. Restrictions must be excluded from domains. Okay, here's the thing. Again, the title, confirming continuity. So if it says on what intervals is the function continuous, that's kind of our goal. Like, where is this particular function continuous? Because we can pick out those pieces that fail and still say, hey, it's continuous here, here, and here, or something. Okay, that's kind of what we're looking at. So first, we're going to just find the domain of these first 4. And then that one is kind of the AP style. Where is the function continuous? And that's where we do the entire analysis. So a little review on notation. Well, we'll do that here in a second. So what should we do first on this one? We're just trying to find the domain. Where is this function defined?
Factor in x at all times.
Yeah, let's factor first. And notice that we're not writing limits. We're not trying to solve per se for anything. We're trying to figure out where this dude is defined. So even if we cancel those x's and then we see, hey, it's just leaving a linear piece, we still have to address the fact that we got rid of something that's causing trouble, which is what? It's the x in the denominator. What can it not be?
0, 0.
It can't be 0. So we're going to show this 2 ways, and you need to be comfortable with both. 2 notations. Meaning you need to be comfortable with reading and writing, but more so reading both of these. So we know x can't be 0, so we can say the domain, and we'll use that fancy R, is all real numbers, but x cannot be 0. So that's an acceptable way to describe the domain, and it's short. What else do we have? What other tools? Do you guys know?
I was just gonna ask, for the graders, we're doing handwritten paper for
Yeah.
the test. If we draw something that's looks similar to that R, we'll know what it is, right?
Well, it has to be similar enough. Yeah.
But I've never been able to write.
Oh well, here's how. Just draw 2 lines, and then draw your R off of the first line.
Alright,
That's all.
thank you.
Yeah. Good. Thanks for asking that. Okay, the other way is interval notation. So we can also write this like if we split this up because it can't be 0. Do you remember union notation? So this is interval notation. We have to break it up at 0, but remember parentheses on the zeros because it can't be 0. So don't mix brackets in here because then this is wrong completely. So infinities always get parentheses, never put a bracket on there. So we're saying all the way to 0 and from 0 all the way, but not 0. That's what that says. So you're going to need to know each one of those. Do you have issues with either one? Are you good for now? Okay. All right, how about this one? What are you expecting to see in our excluded from our domain right now? Yeah, now we have 2 things, right? We have a denominator and we have a radical. And it happens to be an even root. So what can x not be for now?
Zeros.
Okay. That's the easy one right away. X can't be 0. But how do we find the other value? Yeah.
Any value that will link something under the radical negative.
Yep.
So
So what would you do there?
I would say, a 0 under the radical is bad too, right?
No, it's okay.
Okay.
Like square root of 0 is 0.
Yeah, so equal to or less than -6. Oh, no, less than -5.
Okay, so this one, yeah, you can kind of just read it, but I want you to have a strategy for solving for it in case this has some nastiness under there. So you're just going to take the radicand into an inequality to solve. To solve for x. So this one is going to say x plus 5 has to be greater than or equal to 0. It cannot be less than 0, right? That's all that we're saying. And then in this case it's a quick little solve. X is greater than or equal to -5. But it's not always going to be something you can just glance at and solve, right? So keep that in mind. How do we write this? We can't be 0 or also, I mean, it has to be greater than -5. But if we just wrote greater than or equal to -5, that captures 0, doesn't it? So how do we fix that? Do we start with negative infinity? No, because it's got to be greater than -5. So let's start there. Can it be -5?
Yeah.
So bracket -5. Where does this go before we have to stop?
0.
It goes to 0. Can it be 0? No. Union. Where does it pick up again? 0 and goes to? Now it's okay to keep going. And then how about the other notation? It can be -5. Actually, we can't write all real numbers. What am I doing? Let's just go with that one. Because if you write that R, what does it say? Everything except for what we kick out. And we have to kick out basically the entire left half of the number line. after negative that. Alright, next one. What do we have going there? What do I have to be careful of?
Negative numbers.
Negative numbers because of that x.
Four.
Yeah, so also this denominator can't be 0, right? So that specifically excludes 4. And 2 minus root x can't be 0, so let's solve that. And we'll get 2 equals root x, or x equals 4. So that's the other domain restriction. So how would we write this notation? No negatives and no 4. Can it be 0? Yep. So that's a good place to start. So 0 to 4. Can it be 4? No. Can it be above 4?
Yeah.
Yes.
Okay. You could write it like this, like x greater than or equal to 0, x not equal to 4. That's kind of the same idea as with the real number r. We could have done that here as well. It's just, I don't really see it as better. So, I don't know. Just be able to read it both ways, I guess. Let's just say it that way. Okay, this one's tricky. You want to try it?
No.
I'm going to let you try it.
Thank you.
We do know that 4 can't be included, because just right away 4 would make the denominator 0 inside of a log. So we know 4 can't work. Right away. But that's like the denominator condition we have to check, but now we also have to check the log condition, and what is true about it? It can't be what?
Negative
Or 0. Well, what would make the denominator 0? There's one value that would make the denominator 0. Not 4, because 4 would make the denominator 0, which is undefined. But I'm saying there's one value that makes the whole argument, that whole piece inside, 0. And that would be x equals 0, right? Because if this is 0 and that's 0, we get 0 over negative 4, which is 0. So we know that doesn't work as well. We know, what did I write? 4 doesn't what?
Or just
That didn't make much sense. We know 4 doesn't work. We know 0 doesn't work. I'm going to just remind you over here that that is called the argument, the part that's inside. I don't know if that's spelled right, but I'm going with it. I feel like there needs to be an E. So now we just have to address the case of that argument being negative. Okay? So really we need to ask this question and solve it. This takes a little bit more thinking. Where is x over x minus 4 negative? Yeah.
From 0 to 4.
No? It's from 0 to 4. Do I agree with that? Yes, I do. Okay. And where else? So if you plug in a number, like let's pick 1. 1 over 1 minus 4, that would be negative 1/3, right? So we would be negative. Except we're not going to include 0 or 4. So between there. Okay, but where else? Like think below 0. What if I plug in negative 1? What happens? Do you see how that becomes positive because the numerator is negative? So that's kind of weird, right? What if we plug in something like 6? Is that okay? Yeah. What if we keep going down the scale left more, like negative 10? Is there any issues with that? Okay. So is any negative number okay?
Yes.
Do you see how we're kind of thinking through it and talking through it? Do that to yourself too. So is any negative number okay?
Yes.
Yeah. We can think of it this way. This can be negative over negative, or positive over positive. And so we just have to think through what conditions of those numbers make it either one. Okay? And so don't always just throw out, hey, it's negative. That doesn't work. So does everybody see where our interval is breaking? Like we have, okay. So how would you write it? Let's do interval notation first. Oh no, I'll talk at once. I won't hear.
Negative infinity to 0.
Are you guys good at drawing infinity?
No.
Alright, here's what Sonia said. So negative infinity to 0. And then we end up between 0 and 4. We end up with some issues. So where do we pick up from there? And is it bracket or parentheses?
Parentheses.
Can it be bigger than 4?
Yes.
Okay. How would you write that in the other notation? So inequality or inequality notation. How would you write that? Like one of these two.
X is less than 0 or x is greater than 4.
And how about, you said just strictly? No line, right? You said
Yeah.
that? Good. That's a cool looking 0 right there. Alright, how do you feel with the logs?
That was a good one.
That was a good one, yeah. Alright, now let's put it all together with this 5th one. Where is the function continuous? This is a completely different question wording than these last 4, where we were just finding the domain. So where is it continuous? So we need to look at 2 things now. One, we need to look at points of the individual pieces that cause trouble. But then we also need to check the borders, the boundary or the partition points, to see if we're continuous. So it's kind of combining what we did on Tuesday and now adding in the domain restrictions as well. Make sense? So let's just take it piece by piece. In fact, actually, before we do that, I'm going to write that note. So analyze each piece for domain restrictions. Then analyze, I'm having trouble writing stuff. That's right, I got it. Analyze the partition point or boundary for equal, let's call it limit agreement. Actually, I'm just going to call it this for continuity, as in last section. So do you see how this is quite an involved problem? Alright. Also, actually I'll point it out at the end. So does the first piece have any trouble? Any issues here? With domain, I mean. No. So this one is fine. How about this one? Second piece, does it have any domain issues? Okay. This one, x not equal to 7. How about the third piece? Can you do that in your head? Yeah, so 5, right? So no 5, no 7, just based on our piece analysis. Okay, so now we go check just like we did kind of in the not the warm up, but the homework check where we have to analyze if it's continuous. So our points are 0 and 3 is where we're breaking. So limit as x approaches 0 from the left, limit as x approaches 0 from the right, and then 3 from the left, 3 from the right. Lots to do, especially if these functions are harder than they are. Okay, what's the limit as x approaches 0 from the left? And by the way, I'm just going to write f so I don't have to write all that garbage. We'll wait to check function values until we have all these limits to see how they work out. Okay, so from the left of 0, what's our limit? Negative 1/7. Good. From the right of 0, negative 3/7. So we already see an issue there. Come on. There we go. How about 3 from the left? Negative or a positive 3 gets plugged in here. What do we get?
3/4.
But it's 3 minus 7, so negative 3/4. Okay, and let me raise this up just a little. It's too much. Okay, and then 3 from the right. What do we get? That one's a little more involved. Let's just plug it in. 7 times 3 minus 15 over 4 times 3 minus 20, which is 6 over negative 8, so negative 3/4. Okay, so we got some good information. Now that we see that these two limits agree, what else do we need to check? Or show that we checked at least. Keep in mind the definition of continuity. So we've proven that the limits are coming together. What's that last piece?
Check for an F.
Yeah, that f value has to be the same, right? So you need to show, oh sorry, that color is hard to see. Agree, so f of 3 equals, and then we know that it's going to be negative 3/4 because technically we already did that. Okay, but that's now that we've shown it as well. So tell me about where this thing is continuous. What do we have to exclude from the domain, etc.? We know it's not continuous at 0. So now remember, we're not answering where it, like what is the domain. We're saying where is it continuous. We're still going to use an interval, but we're answering a different question. So make sure to clarify that in your brain. So don't just kick out the domain issue. Okay. Sorry, I hate that I have to scroll. This says x is less than or equal to 0. Are we continuous on that interval? Like our first piece starts at negative infinity, technically. Are we continuous up to 0? Yes? Everybody agree? Okay? So let's start writing that. So continuous on negative infinity to 0. Okay, now what? Were we actually continuous up to 0? See how that doesn't work? Because that's not even in the domain of our function. So what should we change?
Negative infinity
There you go. Yeah, we have to actually kick that one out. Gotcha. Not really. I'm not a gotcha guy. Alright. How about between -5 and 0? Are we continuous there? Trevor's giving me the thumbs up. Let's look at, by the way, look at our pieces. We're still operating in this first piece, aren't we? So yes, we're still continuous. This work here proved that we were not continuous at 0, so that's why we're stopping there. Okay, so we are now at 0. We know it's not continuous there, but what about above 0? We have not talked about this yet. It says, yeah.
Is it supposed to be positive 5?
Is it?
Yeah.
Yeah, it is. What? We could have addressed that a long time ago. Alright, so let's just switch these numbers essentially. Clean that up a little bit. Thanks for pointing that out. 15 minutes later. Anyway, so yes, we are continuous up to 0, and then not at 0, but now we're continuous up to 5, and then there's another issue at 5 because we have to throw it out of the domain. Okay, and then are we good? We know -3/4 matched, so at 3 we were continuous. So are we good to say from then on forever?
No.
Why not?
Because of 7.
The darn 7? Yeah. Were you gonna? Well, we did kick out 5. Right there. Okay, so look, this is where AP's gonna get you, so be careful. We can't have 7 in this piece. Does this piece exist where there's a 7? No 7 in there, right? So that's like caution, caution, red flag. I'm gonna say watch out. There's no 7 here. So, is 7 actually okay? Yeah, even though it doesn't work in that piece doesn't exist there. So 7 is fine. So where do we go from here? Yeah, we just keep going up from 5. So, union 5, 2, and 3. There's a lot there. Ask your questions. Do you have any? Feeling okay? Yeah, Devin?
I don't understand why we skip over 7.
Okay. If we went and graphed this whole piecewise and we just want to see it and ignore all the calculus, this piece, in fact, let me kind of sketch what it would look like in maybe a different way. Like, let's say 7 is here, and the piece that we're worried about, it's only being graphed like right here. It doesn't even go over to 7. Something else happens and goes from there, where it's okay. Okay? So I'll go back to that real quick. The interval where this piece is just from 0 to 3. So there is never going to be a 7 plugged into that piece. It'll get plugged in down here. And 7 works down there. Yeah, thanks for asking that. Any other questions about it? So if you go back and read what we said, analyze each piece. That's what the purple check marks or these notations were. Then analyze the partition boundary points. That's what all this work was, to just see if it was continuous at all. And then just make sure you check if these issues even exist where the graph is being graphed. So you could probably expect to see those like that at some time. Questions on that? Can we do 113 just to keep the pace going? Are you guys good with that? It's shorter, and we've kind of done it, sort of. Do you guys need a little break, like a 1 minute or 2 minute break? Okay, let's do that. Alright, so 113, we're just talking a little bit more about how to remove a discontinuity. Which we only had one discontinuity that was even removable. Do you guys remember which one it was?
The whole.
Yeah, it's just a hole. So we need to find the point to plug the hole.
Is that like 49%?
But you recognize that when we have the hole, it's because we have an issue with the denominator. So how do you fill it? You can't just plug in the hole's value to find the y value, right? You can't plug in the x value of the hole, I mean. So, how do you find the x value of the hole? Well, in this case, we'll factor, yep. Factor and find the x coordinate of, and we could potentially have more than one. Find the x coordinate of any, I don't know if this will make sense, but duplicate factors top to bottom. Now in this case there's only one, but you surely you've seen ones where it was multiple, where we had more than one hole. So if we factor this, we get x minus 1 and x plus 1 over x minus 1. So we have a hole at x equals 1. Now I didn't write in here, I said find the x coordinates. But really what I'm saying is the 0 of the duplicate factor, right? So I might clarify that over here. So set it equal to 0 and solve. Alright, how about the y value? So we know the x value. But you notice if we go plug this x value back into the function, we have a 0 denominator, which doesn't tell us the y value. So how do we do that? Thinking calculus. What would tell us that point? Like we're trucking along. Remember, we're just talking about a hole. In fact, why don't you draw this little graph? Some version of this. You could either have just a hole, or you could have something filled in elsewhere. Either one. Okay? But regardless, we're trucking along here and suddenly we run into an issue, but then everything's fine afterwards. And I'm kind of trying to lead you to say what is true about that point. The limit exists, right? And is that y value? Right? So let's use that instead of messing with this function. The limit exists there. Because it's a hole, like we're not worried about jumps or infinite discontinuities, it's a hole. So the limit definitely exists there. And is the y value of the hole. So we're just going to take the limit as x approaches, what were we at? As x approaches 1 of f, which is just to say plug 1 into the simplified function. But let's go ahead and show that. Okay. Okay. Which is 1 plus 1, which is 2. So our coordinate to remove use 1, 2. That is a single point that we could plug into that hole, and now we are continuous the entire way. Okay, so we removed a discontinuity, and now the function is continuous. It would look something like defining, if I said write the function now. Now I'm not saying that here, but the function would be, if we wanted it continuous, it would be x squared, and I'm doing it kind of shorthand, for x not equal to 1, and then it would be 2 for x equal to 1, and we would have our little brace there. So thinking of a piecewise definition, that is the continuous function that we just fixed. Okay? Now you can see why maybe those limit strategies might help us do this, because when I say use the limit, maybe we have to use some tricks to figure out that y coordinate. Alright, next one. If the function, let's do this real quick, is continuous for all real numbers, and if f of x is defined there when x is not equal to -4, so thinking something like this, right? Then f of -4 is, meaning when x equals -4, what are we going to put right there? Okay, so we're building this piecewise where the function is continuous. How do we do that? Well, we need to know where the x value is. It tells us, kind of in this one, that it's at -4. So the x coordinate of our hole is x equals -4. The y coordinate, how do we find that? What did we just write up there? No, we can't plug it in, because that would just make this 0.
Factor.
Before we factor, what do we need to write? What does that say right up there? This is always true. If we have a hole, that will always be true. Huh?
Finding the hole.
Finding the limit at that point. Is that what you mean? Okay, well I'm asking, I want everybody to be super specific. So we need to write it out as limit as x approaches what? -4 of x squared plus 6x plus 8 over x plus 4. Okay? Is it okay to write equals the limit again? Here. Yeah, because I'm just factoring. Okay, now what? Do I need to write limit again? Can I plug in? Yeah. So we can just write -4 plus 2, because those two factors cancel. Okay, and we get -2. So f of -4 is -2. Why? Pedro, can you explain why? And how do we know?
Well, basically, because we just did a limit, so we basically canceled the problem once we just caused the whole basically.
Okay, Kyla, how come the limit works? Yeah, it's not like jumping, right? So the limit exists. It's also not infinite. It's just running along, skips the hole, and keeps going. So that's always true. If we're plugging a hole, there's a hole, which means the limit is always going to exist. Alright, a little bit different version of what we saw before, but it's not that much different. So let f be the function, this piecewise, what is the value of a? For what value of a is f continuous when x equals 6? We kind of looked at this last time, I guess. What do you guys think? What did we do then? So thinking of Tuesday's work. We just had this, yeah.
always set them equal to each other.
Yeah, because if they're going to be continuous, those two pieces, whatever their function rules are, those two pieces have to give us the same value. Okay, right now we have two variables, x and a. Obviously we're evaluating this at x equals 6, but if you plug that in, you're stuck because you get a 0 denominator. So what do we do there?
Factor.
In this one, you know, in all of these we have factored. It's not always going to be factoring, but you guys doing good at your factoring? That is an ugly A. Okay, so we end up with just x plus 3 equals a. And now we can plug in 6 because we're not worried about it being broken. So if a is 9, then that's the y value that makes that work. Now, could that be another function? Like, could this say 3a plus 2 or something? Yeah? Just know that it's not just always going to be a single letter. So does that feel somewhat familiar from the work we just did? Okay. You guys good? Can't really read you sometimes. I don't know if you're tired, bored, confused. It's all the same facial expression. Huh?
All of the above.
I'm going to give you a rate. So, 112. I'm going to ask you to rate fist. I'm clueless to 5. I get this. Come let me teach you. 112, the stuff we just did a little bit ago, where we found what intervals the function was continuous on. That's, to me, that was the biggest idea from that section. So question 5, I think it was on there, if you need to look back. So rate yourself, and I know you haven't tried it yet, so that's just, it's hard to rate until you try. But just this way it gives me some feedback. Okay, so I think we're in the right spot for that. And then how about this stuff? Plugging holes. Okay, so about the same, a little better on that. Alright, well, circle the following on those two sections. So on section 12, Google Classroom is really taking me minutes. Anybody else having trouble? Alright, on 112, do 5, 7, 10, 11, and the test prep. 5, 7, 10, 11, test prep. And then on 13, I don't know, I might change this a little bit. Yes. Do 11, 12, actually let's do 10 through the end. So 10 through 14. And you have a few minutes if you want to do it now.
It's just something I just got. So I don't read it.
But yeah, like for the
Oh, I just got it.